Audio Jungle. Audio Jungle.
Right. So we have a potential function. Potential function. Always remember, just like a stream function we had seen, so potential function also here we have, and with particular purpose we have to also use potential function. And always remember, potential function is what denoted by phi. It is also a scalar function. It is basically used to study irrotational flow. Used to study irrotational flow. Used to study irrotational flow, right? And very important, the difference between potential function and stream function is 3D flow. Is used to study 3D flow. Okay, it is used to study 3D flow. All right, now, so like how to define it? Uh, it is defined. It is defined. Uh, it is defined as a scalar function of space and time. Okay, space and time, such that its derivative in any direction gives the velocity in that direction. Okay, and it is denoted by phi. So this is the very simple basic definition. Like mathematically how to get it, that is important. So this potential function, which is denoted by phi, it's a function of space and time, right? Function of space x, y, z, and time t. All right, because it is valid for 3D, so definitely we have to talk x, y, z axis. X, y, and z. In direction of x, velocity component is u. In direction of y, it is v. In direction of z, it is w. If you talk about the velocity vector v, ui, vj, wk, right? ui, vj, and wk, these are the uvw, these are the velocity component in x direction, in direction x, in direction y, in direction z, right? And if you define the potential function, so it is said, if you take derivative of potential function in any direction, so we'll get velocity in that direction. That is the definition theoretically. And mathematically you can write the formula also. What is the formula now? What mathematically you can write? What mathematically you can write? It's very simple. See, it is said, if you take the derivative of potential function, see this, if you take the derivative of potential function in any direction, gives the velocity in that direction. Very simple. Means if you are taking derivative in direction of x, if you are taking derivative of potential function in direction of x, so what is the velocity you will get? You will get velocity in x direction. What is the velocity in x direction? It's u. So you will get u here. Similarly, if you take derivative of potential function in y direction, you will get velocity in the same direction, that is v. And here also, if you take the derivative of potential function in z direction, then velocity will get in the same direction. So it's nothing but uvw, that velocity you can get. It's very simple. You are taking the derivative. You are taking the derivative in x, y, and z. Very simple. Okay, x, y, and z, and obviously x direction you have seen the velocity component is nothing but u. This is what v, and this is what w, right? So potential function is now defined. Dou phi by dou x is nothing but u, dou phi by dou y is nothing but v, dou phi by dou z is nothing but w. This is what uvw, like in this way you have to calculate. It's very important. It's very, very important. Okay, right? Velocity potential function in polar coordinate. Okay, in polar coordinate. Here, this what you had seen, this was the velocity potential function. It was for the Cartesian coordinate. See this, what you have seen here, this is the Cartesian coordinate. X, y, z is nothing but Cartesian coordinate, right? It's a Cartesian coordinate. So whatever the formula you have got here, this is nothing but for Cartesian coordinate, right? It's Cartesian coordinate. The same formula of the potential function you have to write for the polar coordinate also. So just like a stream function you had seen polar coordinate, so here also we have a polar coordinate, and this polar coordinate you can, last class also I had explained, suppose this is what r and theta. So this is nothing but r, and this angle is nothing but theta, r and theta, right? So in polar coordinate also we can write the velocity potential function. So where will be the tangential velocity? It will be in direction of theta. So direction of theta is nothing but this is the direction of theta. So this is what v theta here. Okay, where is vr? It is parallel to radial direction, so vr will be parallel to radial direction. So you have to draw the radial direction parallel to radial direction. This is nothing but parallel to radial direction, which is nothing but vr. Then where is the v? That is resultant velocity vector v. So it will be the sum of, sorry, it will be the sum of vr and v theta. So this is nothing but v vector. This is nothing but v vector. Okay, so here it is clear. V vector is nothing but resultant sum of radial plus tangential, right? So what will be the radial component here? Just like a stream function you had written in radial direction as well as in tangential direction. So here also, obviously here also you have to write for the potential function as well. Now, so what is the VR? What is the VR? Simple. VR is nothing but radial velocity. I need to write also. Radial velocity, which is nothing but VR, and tangential velocity, which is nothing but V theta. Okay. Radial velocity and tangential velocity. Any idea? Is nothing but VR is nothing but dou phi by dou theta. Dou phi by dou theta when you are taking VR. Okay, when you are taking VR, it's nothing but sorry, no, it's a mistake, because if you are taking derivative of potential function in radial direction, then you will get velocity in radial direction. That is the potential function. Okay, I have taken as a stream function, so just opposite I have written. Radial means if you are taking derivative of potential function in radial direction, then only you will get velocity in radial direction. So if it is VR, then this is dou phi by dou r. And this the same thing you have written, right? Like here also you have written, see, if you are taking derivative with respect to x, you will get velocity component in x. So same thing you have to use for the radial component also. And if you talk about v theta, so obviously dou phi by dou theta will come. But again, I have told you in case of the stream function also, if you are taking theta in denominators to make the unit proper, uh, you have to multiply by 1 by r also. So now this unit will be correct. This unit will be correct now, because again the same unit, phi unit also, it's a meter square per second. It's a meter square per second. So if you check dou phi by dou theta, theta we do not have any unit, so meter square per second, and r if you multiply 1 by r, if you multiply, then again meter will come in denominator. So meter square per second divided by meter. So meter cancel out. You will get meter per second. That is the unit of velocity, right? So that formula you need to remember. That formula you need to remember here. Now coming to, see, this formula is now, it is formulated. It is now formulated. Now, so coming to this two formula, what I have written, it's a Cartesian and radial. Cartesian coordinate and polar coordinate and polar coordinate. So in short, I will write u is equal to dou phi by dou x, dou phi by dou y, dou phi by dou z. Then similarly, you can write radial velocity, so dou phi by dou r. Tangential velocity is nothing but v theta, it's a 1 by r dou phi by dou. This is the outcome you need to remember. Okay, you need to remember this formula, right? Now as I have already told you, like few features for the potential function we have. So this one you need to remember, features of potential function. Features of potential function, right? So now the first point we have to check, because phi is the function of, it is valid for 3D flow, so it's a function of x, y, z, no doubt. But if you go for the 3D calculation, again calculation will be very lengthy. So you take 2D, just for understanding, you take 2D and then you can convert into 3D also, right? So it is possible to take in 2D and then convert into 3D. So because 3D If you go for the calculation, then it will be a little bit difficult. Okay, not impossible, little bit difficult. So why will go in difficult mode? Simply will take 2D. This is for 3D, and if you take 2D, then it is f of x y. This is now 2D, right? This is now 2D. So coming to this analysis, what is the total derivative? Because potential function is what depending on x and y now. So total derivative d phi is nothing but dou phi by dou x into dx, dou phi by dou y into dy, right? Then what is d phi? It's dou phi by dou x. What is dou phi by dou x? It is u. It is u, and then this is nothing but dx. This is nothing but dx. This is v, nothing but dy. If finally you got this equation, right? You got this equation. This is very unique result. Basically, this is very unique result. Now, if you check, uh, for the Cartesian coordinate, u dx d phi is equal to u dx plus v dy we got. And now you also check if circulation, I don't know if you remember or not, circulation was v theta into ds, and you had written for this also, it was u dx plus v dy, right? So from here also you can consider it is, if it is closed contour, then what you will have? You will have circulation which is nothing but d phi u dx plus v dy, right? This is the one important result you got here. This one important result you got here, okay? Circulation, no? For that reason, hope you understood why this potential function is used for irrotational flow, okay? Right, now, if you check, in this case, if you check, uh, what is the mean of d phi here you got? D phi is equal to what you got? U dx, v dy you got, right? Now, if I want to say d phi, which is nothing but, suppose any function I can take, like just like for a streamline we had seen, stream function was constant, psi was constant. So we can say, because this is the d phi, I can say phi is what? Constant. If phi is what? Constant, then there will be one line, okay? Just like when psi was constant, stream function was constant, then there was one line. That line was streamline. So similarly, phi is what? Suppose constant. It is now going to define, basically, if phi is what somewhere for any line is what? Constant, then we can define this. Then what is the mean of it? Its meaning is very clear. A line of constant potential function, is termed as equipotential lines, okay? Termed as equipotential line. So it's very clear now. If I say equipotential line, so immediately you have to understand, for equipotential line, phi will be constant. So so the potential function phi is constant if potential function phi, if potential function phi is what? Constant, and that is for equipotential line. That is for equipotential line. Then what is the d phi? D phi will be 0. Okay, d phi will be 0. So now onward we can say whatever the equation we have, d phi is equal to u dx plus v dy for for equipotential line. For equipotential line, d phi becomes 0 because for equipotential line phi is constant. So for equipotential line d phi becomes 0. It's 0 u dx plus v dy, right? Now onward, here you can say, because suppose this is the coordinate system, this is what coordinate x and this is y. So definitely this, any distance you can take, this is what dy, and this distance you can take, this is what dx. If I say this value, so it's nothing but theta. So this value is nothing but, what is the tan theta? Tan theta is nothing but dy by dx. So this dy by dx called slope. What it is called? Slope. Okay, slope of this slope, tan theta is called slope, which is denoted by m. So this is the slope. Now you can write slope of equipotential line. So what is that? It's nothing but dy by dx for phi is equal to constant. Phi is equal to constant means equipotential line. So what is the slope you got? Check. If you see here how to write dy by dx, it's nothing but v dy is equal to, from here you can say it's nothing but v dy is equal to minus of u dx. So what is dy by dx? It's nothing but minus u by v, minus u by v. This is the slope of the equipotential line. It's very, very important. Okay, you need to remember, this is very, very important, right? Now coming to the next point, this is the first point here you got. Coming to the next point, what is the another feature of it? If you see the continuity equation in 3D flow, then what will be that? It's nothing but dou u by dou x plus dou y by dou y, dou v by dou y plus dou w by, this is for 2D but I'm writing for 3D, anything you can write, it's your choice, dou w by dou z. And if it is incompressible, for incompressible flow, continuity equation for incompressible, if it is incompressible, then this dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Okay, now the same for 2D also you can write. For 2D it will be dou u by dou x plus dou v by dou y is equal to 0. Now you just satisfy, uh, we have to satisfy potential function to this continuity equation, then what we'll get? So it's a dou by dou x, u is nothing but, uh, we are writing the value of u, which is nothing but dou phi by dou x. Similarly, dou by dou y, v value is nothing but dou phi by dou y is equal to 0. Okay, means dou square phi by dou x square, dou square phi by dou y square is equal to 0. Okay, what you have did, you simply here, simply you kept u is equal to dou phi by dou x, v is equal to dou phi by dou y. Similarly, we can dou phi by dou z also, right? So now this is for the 2D you have written here. But you know very well that potential function is also valid for 3D. So for 3D, what will be this equation? What will be this equation for 3D? It will be dou square phi by dou x square, dou square phi by dou y square, dou square phi by. Now you can see this is nothing but dou square by dou x square, dou square by dou y square, dou square by dou z square. Here you can write phi equal to 0. If you see, this is the Laplace operator grad square. Grad square phi is equal to 0. Now if you are getting grad square phi is equal to 0, this is called as Laplace equation. This is Laplace equation. Why it is called Laplace? Because this delta is the Laplace operator basically. So this is the Laplace equation for potential function. Potential function. Now what is the mean of it? If the potential function is what satisfied the continuity equation, or you can say if Laplace equation exists. If Laplace equation exists, it means if Laplace equation is exist, then it means that there is the possible flow. Flow is continuous. Okay, flow is possible. Flow is what continuous. That's the mean of it, right? Because grad square phi is equal to 0. If you have proved this, then how it comes? This grad square phi, how this equation comes? So this equation comes after satisfying the continuity equation. So here I can write grad square phi. Here I can write grad square phi is equal to 0. What it indicates? So it indicates that if velocity potential function phi satisfy the Laplace equation. Laplace equation. It is a case of case of possible fluid flow. Okay, it means continuity of flow. It means continuity of flow means flow is what? Continuous. That means there is a possible case of flow. That's the mean of it. This is very important outcome you got here. Third point I'm going to discuss. Third point, if you want to satisfy this potential function to the angular velocity. So for xy plane, what is the angular velocity? Obviously it will be omega z, right? Because this is the xy plane here, x and y. So perpendicular axis will be z, and about this z will have angular velocity omega z. So what is the omega z? It's a 1/2. So v and mu. This is the formula of omega z. Now you check it. You can write omega z is equal to 1/2 dou by dou x. V is nothing but dou phi by dou y. U is nothing but dou phi by dou x. We can have here 1/2 dou square phi by dou x dou y minus dou square phi dou y by dou x. It's a omega z, right? Now for irrotational flow, the same equation what you have got here. If I say for irrotational flow, here only I can write for irrotational flow, omega z will be 0. So for irrotational flow, what you will get? See, you will get dou square pi by dou x by dou y, dou square pi dou y by dou x. So if you want to check, this is the way, okay, to find out that flow is what rotational or irrotational. So velocity potential satisfied condition, okay, velocity potential satisfies the condition for irrotational flow. Okay, now you just think about it. If potential function exists, then it will satisfy the continuity equation, because if flow is possible, then you have to go for the continuity equation itself a mass conservation, and it is saying the flow is what possible, flow is what continuous. So whenever any function is what satisfying the continuity equation, it means there is the existence of the flow, the possible case of flow. Now if you check this equation, this equation is what continuity equation, but this continuity equation for what? So this equation is what continuity equation, and it is for the incompressible flow. If you remember, this is for the incompressible flow. Okay, incompressible flow. So any irrotational incompressible flow has a velocity potential function, okay, and a stream function. Both satisfy the Laplace equation, okay, because for irrotational flow we are using potential function, for incompressible flow we are using stream function, right? But if you talk about the Laplace equation, so both stream function and potential function both are satisfying the Laplace equation. So now another kind of flow name is what generated here, that is called potential flow, and that potential flow will consider uh, two things: irrotational and incompressible flow. This is velocity potential I have explained you, velocity potential function I have explained you. But if you go for the potential flow, so potential flow is basically potential flow. So potential flow is basically the flow which consists both incompressible, incompressible. Now I was talking about the potential function here. So potential flow. So velocity potential function is different and potential flow is different. Don't get confused. So if I'm saying potential flow, so potential flow is the flow where the flow is what considering both incompressible and irrotational flow. Incompressible and irrotational flow, once you combine both, then this flow will called as a potential flow. Okay, this flow will be called as a potential flow. This equation will be called as a potential flow. And always remember, potential flow is there, it means psi and phi both will be existing, because if it is incompressible flow, so for incompressible flow stream function will be existing here, and for irrotational flow phi, means if irrotational flow is there, then phi will be existing, as well as we can say to define the irrotational flow we have to use the velocity potential function, and to define incompressible flow we have to use stream function. And obviously once potential flow we have, then psi and phi both will be using there. Based on this analysis, we have one equation which is called CR equation. What it is called? CR equation, that is Cauchy-Riemann equation. Cauchy-Riemann equation, it is very important. Okay, so here we can write Cauchy-Riemann equation, which is called CR equation. CR equation. Okay, now listen carefully. 2-3 points you need to remember, like you got here, like potential function phi exist only for irrotational flow. Up to here you got it. Irrotational flow, number one. Number two, stream function psi applies to both rotational and irrotational. Stream function is valid for rotational and irrotational. Okay, but the condition is stream function valid only for incompressible flow. So the flow has to be, if stream function is existing, the flow has to be steady and incompressible, because stream function is what valid for incompressible flow. Once it is incompressible flow, steady and incompressible flow, then it doesn't mean it is rotational for or irrotational force. For stream function there is no problem, but for the potential function, if potential function is what existing, it means the flow is what irrotational. For rotational flow, potential function will not exist. Okay, for the rotational flow, potential function will not exist. And now you got it, you got the point. What is the common here? The common point is, if you see for the potential function, so common is what irrotational flow, and for stream function also irrotational flow is what common. Means for stream function, it only condition it should be incompressible flow, it should be steady and incompressible flow, doesn't matter rotational or irrotational. But for potential function it should be irrotational flow. So means irrotational flow is what common for both, right? So here we can say for third point, I can mention here only, this is very important. For irrotational flow, both stream function and potential function satisfy Laplace equation. You have seen Laplace equation, both are satisfying. Okay, Laplace equation. Consequently, if it is irrotational, then it can be interchangeable. That is the very important point. So Laplace equation, so here you can write consequently they are means phi and psi are interchangeable. When it is interchangeable, when it is irrotational flow, because for irrotational flow both are satisfying, potential function is satisfying and stream function is what satisfying for the irrotational flow, both are satisfying. See, so it means if it is irrotational flow, then both are interchangeable. So who comes to this result? That scientist named Cauchy-Riemann. So because of their name only, its equation called as a Cauchy-Riemann equation, CR equation. So now onward you have to remember relation between stream function psi and potential function phi we can develop for steady, irrotational, and incompressible flow. That is steady, irrotational, and incompressible, called as a potential flow. Here I had not written steady because we are assuming all the flow are steady flow until unless we are not going unsteady, because unsteady is itself very difficult condition. Why? Because already we have a 3D, then again one more dimension, that is time. If you take, then it will be 4D, so problem will be much more complicated. For that reason we always consider it is steady, so time dimension will be automatically eliminated. Means anything which is not changing with respect to time called steady. So we are considering whatever the properties, maybe flow property or fluid property, they are not changing with respect to time. So time dimension automatically eliminated. Okay. So for that reason we are saying steady. So steady I am saying or not saying, but it is considered as a steady flow. So always remember, potential flow is steady, incompressible, and irrotational flow. Okay. Anyway, so now automatically, if you want to interchange psi, phi, then what should be the flow? The flow should be for steady, incompressible, and irrotational, and irrotational flow. We can interchange psi and phi. How we can interchange? See the result, you will understand. We have u is equal to minus dou psi by dou y, and u is equal to also it's a dou pi by dou x. V is equal to, we have dou psi by dou x, and also v is equal to dou phi by dou y, right? Similarly, this is the Cartesian coordinate, and this similarly we can write in polar coordinate also. So this is the CR equation in Cartesian coordinate. Okay, always remember, this is very important equation. So here you can interchange. How you can interchange? You can write minus dou psi by dou y is equal to dou pi by dou x. This you got from the CR equation, and you can write dou psi by dou x is equal to dou pi by, this is the CR equation. Okay, means your psi and psi value and phi value must be interchangeable when there is the steady, incompressible, and irrotational flow. Similarly, you can write CR equation. You can write CR equation in polar coordinate. So how you can write? It's a simple formula only. The formula is v theta, tangential velocity, minus dou psi by dou r, and this is also 1 upon r dou phi by dou r. Then radial component, it's a dou psi by dou theta 1 by r, then it is nothing but dou phi by dou r. Here also you can interchange 1 by r is equal 1 by r dou phi by dou r is equal to dou psi by dou r in minus, and dou phi by dou r is equal to 1 by r dou psi by dou theta. It is interchangeable now, right? So this comes from the CR equation, which is called Cauchy-Riemann equation. Now also we have to write the slope of streamline. How to write slope of streamline? Simple. Slope of streamline, you can write here slope of streamline and equipotential line. How to write it? See, we know streamline first. Streamline. What is psi? Function of x comma y. Right? What we can write? D psi is equal to dou psi by dou x dx dou psi by dou y dy. What is d psi by dx? If you see here, dou psi by dou x here only, dou psi by dou x, it's nothing but v. So v dx dou psi by dou y minus u dy is d psi. Okay. So along a streamline, psi is constant. You have seen that. So what is the d psi? It will be 0. Along streamline, always remember stream function psi is constant. We already have seen in last lecture. So along streamline d psi will be 0, right? So if it is 0, then what will have? V dx minus u dy. What is dy by dx? Which is the slope of streamline, and for streamline psi is constant. What is dy by dx? It's nothing but v by u. This is the equation number 1. Right? Now we'll go for equipotential line. Equipotential line. So we can write a stream function is the function of x comma y. What is d phi? It's dou phi by dou x dx. Just now I have written, but it will take very less time. So again I am writing. What is dou phi by dou x? It's a u dx. It's a v dy dou phi. Right? D phi is equal to it's a u dx plus v dy. Okay. So along equipotential line, just now you have seen phi is what? Constant. If phi is what? Constant, then what will be d phi along equipotential line? It will be 0. So we can keep here, it's nothing but 0 u dx plus v dy. What is dy by dx? It's a slope of equipotential line. It's nothing but dy by dx. It's nothing but minus u by v. This is equation number 2. Both equation you can see, this is the slope of you can say stream line, so m1, and this is the slope of equipotential line, which is m2. Now if you see from equation 1 and 2, from equation 1 and 2 you have seen here, we can write m1 into m2. So see what we'll get. What is the m1? It's v by u. Okay, so dou y by dou x, psi is equal to constant, and dy by dx, phi is equal to constant. What is the value of m1 into m2? What is dy by dx? Just now here you have written, forget, v by u into what is dy by dx? Minus u by v. See this value, it's nothing but m1 into m2 minus 1. For the two lines, if the product of slope is minus 1, then what this property is called? What is the conclusion? Conclusion is very simple, that the product of slope of equipotential and slope of a streamline at the point of intersection where both are crossing to each other, it becomes minus 1. That product of slope becomes minus 1. That means the equipotential lines are, here I will write equipotential lines are orthogonal to the streamlines. at all points of intersection. Okay, okay, intersection, except except at except at stagnation point, except at stagnation point. Okay, except at stagnation point, all points, streamlines and equipotential lines are orthogonal. Orthogonal means perpendicular to each other. Okay, means if I say this is what is streamline, this is what is streamline. See, I can say this is psi 1, psi 2, psi 3, psi 4. If I say this is the streamline, right? If I say draw the equipotential line, the equipotential line will be orthogonal to the streamlines, means it's perpendicular to streamline everywhere. So this will be phi 1, phi 2, phi 3, phi 4. And everywhere it will be 90 degree. Okay, anywhere if you check point of intersection, it will be orthogonal. Orthogonal means perpendicular everywhere. Okay, so this is very important conclusion you got here, that streamline, these are the equipotential line. Okay, I have to write somewhere, these are equipotential lines and these are streamlines. Okay, always remember. And if this thing is what happening, so best example is the flownet. Okay, flownet is the example of this. We have a flownet. So basically a grid obtained by drawing a series of equipotential lines, and this is now a streamline here. Multiple line you can draw like this. This is the streamline, multiple streamline. Okay, and drawing of series of equipotential line and streamline known as flownet. This is known as flownet. Okay, so this grid you are getting now, phi 1, phi 2, phi 3. So this is nothing but the series of equipotential line and streamline. These are called as a flownet. So basically flownet is the one of the method for solving uh, or analyzing 2D irrotational flow problem. Okay, so flownet are drawn in such a way that difference between stream function of two successive streamlines are same. The discharge to successive streamline is constant. I told you that two streamline, if you are taking psi 1, psi 2 and psi 1, psi 2, psi 3, so between any two streamlines, whatever the difference of a streamline, it's nothing but discharge. Already I had explained. So basically this flownet is nothing but it's a grid basically made by the uh, series of streamline and as well as equipotential line, and this will be used to analyze the 2D flow. Okay, 2D flow, irrotational flow, but it should be 2D, right? So this part is done.